This video is probably one of the first really applicable topics that you can come across in calculus, and it's talking about velocity and acceleration. So first of all, there's a position function, and for some reason they use S for position. You'd think they'd use P, but P is usually for population, but position over some time is given by this function, negative 16t squared plus v naught, or v sub 0, times t, plus s naught, or s sub 0. And these letters, this means time, v naught means initial velocity, and s naught, which mean anytime you see this little 0, that means initial. So this would be initial position, since s means position. So this is for free falling objects. Which means any object that falls through the air, basically. So if I had an airplane that was flying for our country, and this airplane decides he wants to drop a bomb on this tank down here, and the airplane is maybe flying at an altitude of 5,000 feet. If I wanted to know how long would it take that bomb to hit the ground, I would come over here to my position function, and I would say my position function for this particular problem is s of t equals negative 16 t squared plus my initial velocity. In this case, since the airplane is just dropping the bomb, there's no initial velocity, so that's 0 times t, plus the initial position is 5,000 feet high. When would this bomb hit the ground? Well, the ground's position is 0. So I want to set my position equal to 0 and solve for t. 0 times t is 0, so this part goes away. So I would move the 5,000 over here, or move the 16t squared over here. Divide each side by 16. And then to find t all by itself, I would take the square root of each side, plus or minus for a square root, 5,000 over 16, whatever number that is. Now you notice a negative square root for time. I don't need that time value because there's no such thing as negative time, and so I'll just ignore that and I'll just use the positive value. So this would be 17.67 seconds. So that's how many seconds it would take for this bomb to hit this tank if it was just dropped. But you could maybe assume that this gets shot out of the airplane with an initial velocity of so much. Well, then you would put your initial velocity right here, and then it would come down here, and then it would come down here, and you would have to use something like the quadratic formula sometimes to solve this for t, or some other method like factoring. But either way, you just solve this for t. So let's say I wanted to know something like how hard or how fast would the bomb be falling when it hit the tank. So we already know from a minute ago that this will hit the tank at about 17.7 seconds. And so, if I wanted to know what would the velocity be when the bomb's down here on the ground, it turns out that the rate at which a position changes, since a derivative is a rate of change, I'm going to take the derivative of position, which is actually called velocity. And now I have a velocity function if I just take the derivative of all this with the power rule. So this would be negative 32t plus 0 plus 0. So you see here I have a velocity function where if I wanted to know the velocity of this bomb at any time, I could plug it into this velocity function. So if I wanted to know the velocity when time is 17.7, which is when the bomb was on the ground, the velocity at 17.7 is negative 32 times 17.7, which is negative 566.4, and the units are feet per second. Since this is a rate of change, you're saying how many feet every second is the rate of this position changing, and that's this right here. It turns out that the derivative of velocity is the rate at which the velocity changes, and that is acceleration. So if I wanted to know the acceleration of the bomb, that's negative 32. Notice the t goes away, the derivative of negative 32t is negative 32. If I wanted to know the acceleration of the bomb at 17.7 seconds, well, the acceleration is always negative 32. So the answer would be negative 32 feet per second per second. So let's say the high school's t-shirt cannon shoots straight up. Let's say it shoots a t-shirt out of the cannon with an initial velocity of 100 feet per second. And that t-shirt goes up for a while and then comes back down for a while. And I wanted to know how long would it take for the t-shirt to be back on the ground. All I would have to do is say, I'll come up here to my position function, negative 16t squared plus my initial velocity, which is 100, times t, plus my initial position. Well, if you measured how high the t-shirt is when it leaves the cannon, we'll say that's about 4 feet. And I want to set that position equal to 0 because that's when the t-shirt lands on the ground again. There are two ways to solve this. You could either factor this, if this will factor, or you can use the quadratic formula. So time equals negative b plus or minus the square root b squared minus 4ac all over 2a. This is the quadratic formula. I don't know if you remember that, but this is A, this is B, and this is C. If you execute the quadratic formula correctly on this one, you will get 6.29 seconds, or negative 0.039 seconds, which would be actually behind the t-shirt cannon, so we're going to ignore this one. You go with 6.29 seconds is how long it would take this t-shirt to come back to the ground. If you wanted to know the velocity when the t-shirt hits the ground, you would find your velocity by taking the derivative of position, negative 32t plus 100. See, here's my position function. The derivative of position's velocity, if I want to know the velocity at 6.29, I'd say negative 32 times 6.29 plus 100, and that would equal, so that equals negative 101.28 feet per second. Since we're talking about velocity, the units would be feet per second. So this will conclude the first video on velocity and acceleration.